Hello friends, this is Professor Pathakar, and in our today's lecture we are going to start a new chapter of heat transfer subject, which is extended surface or fins. This is very interesting and very easy chapter of heat transfer subject. So let's start with the first slide. We know that whenever there is a convection heat transfer between a solid surface and the fluid, the heat transfer rate can easily calculated by equation HA delta T, where H is a convective heat transfer coefficient, A is a surface area of the body from where heat transfer takes place, Ts is a surface temperature, and T infinite is a temperature of the fluid. So, to increase the heat transfer rate by convection, which is directly proportional to convective heat transfer coefficient, surface area and temperature difference, we have to increase temperature difference or surface area or value of H. By increasing either of this value, we can increase the value of Q. But in most of the cases, the temperature difference is in not our hand. So there are remaining two parameters, H and AS. H is a convective heat transfer coefficient which is dependent on so many parameters and mostly depend on either it is forced convection or free convection. To make it a forced convection, we need a external arrangement like pump or fan, so which is not a practical solution to increase convective heat transfer rate. So we have only one option to increase heat transfer rate by convection, is to increase the surface area. So to increase the surface area of the any system, there are extended surfaces are used, which is known as the fins. Okay, so this is general introduction. What is fins? So it is extended surfaces which is used to increase the surface area of any system to increase the heat transfer rate by convection mode. Okay, so to increase the convective heat transfer rate by extended surface, the material should be highly conductive, because the highly conductive material can absorb maximum heat through conduction from the body, from the system, and release that heat to the surrounding by convection. So the material of the fin should be highly conductive like aluminum. So fins is used to enhance heat transfer rate from surface by exposing larger surface areas to convection and radiation, because we know that convection and radiation is a surface phenomena. The maximum surface area, the maximum convection and radiation will take place. There are some geometry of fins, or we can say the types of fins. This is a simple rectangular fin, some triangle cross-sectional area type of fin, say a disc type fin, taper type fins. There are some innovative different types of fins are shown in figure. So you can see that in this all types of fin, the only final goal is to increase the surface area of the system to increase convective heat transfer rate. Here we can see that this is a plain wall and one rectangular fin is attached to this wall to increase the surface area. In this case, what will happen? This fin, which is a highly thermal conductive material, which have high thermal conductivity, so it will absorb heat from this surface, from this base wall through conduction, and release that heat to this surrounding environment by convection method from this surface area, which is in upper part, as well as from lower portion of this fin. So fin is used, in summary we can say that fin is used to increase the surface area of the system to increase heat transfer rate, so that the temperature of any system will not exceed a particular upper limit of the temperature. Okay, now to design the fin for any system, knowledge of temperature distribution along the fin is necessary. So for that analysis, let's take some assumption that always in fins that always steady state heat conduction take place. Second, uniform heat transfer coefficient throughout the surface of the fin. Third assumption is there is no heat generation within the fin. Fourth is thermal conductivity of the fin material is constant throughout the fin. Negligible thermal contact resistance between the base material and the fin. Next assumption is heat conduction is always in a one dimension. And the last, there is a negligible radiation. Mostly we will consider that heat transfer takes place by convection. So these are some assumptions before starting designing of fins. Let's take one simple example of rectangular fin. Here in figure we can see that there is one wall whose base temperature is TO, which is much higher, and one rectangular fin is attached to this wall to increase heat transfer rate. So what will happen? This fin, which is highly thermal conductive, will take heat from this base wall through a conduction. So here we can see that it is a Q conduction in this X direction. So heat will transfer from base wall to the fin by conduction mode because they both are in a physical contact. Now as this heat travel along the X direction, this surface of the fin is open to the environment, open to the surrounding. So simultaneously convection from the upper part and lower part of the fin takes place. So as we are moving forward to this direction, the temperature will drop, and at some point the temperature of the fin's surface and the temperature of the surrounding will become same, and there is no temperature difference. So there is no heat transfer after some length of the fin. Okay, this is a simple view of the rectangular fin which is attached to a base whose temperature is TO. Now let's make a mathematical model, or let's make a derivation from this. In this figure there is a wall whose temperature is TO, which is our base temperature. One rectangular fin with a high thermal conductivity is attached with this wall to increase convective heat transfer rate. This is a X direction. So what will happen when we attach this fin to this base wall? Let's denote some parameter. L is the length of the fin, which we can see from the figure. This L is a total length of the fin. B is a width of the fin. Okay. Y is this is a thickness of the fin. P is a perimeter of the fin, which is 2B plus Y. ACS is a cross-sectional area, which is B into Y, width and the thickness, width multiplied by thickness. TO, this is the base temperature of the wall. TA is the atmospheric temperature, or we can say that ambient temperature, surrounding fluid temperature, air temperature. K is thermal conductivity of this fin material, and H is a convective heat transfer coefficient. Okay. Now we can see here from the figure what will happen. First, the heat will conducted from this wall to this fin, and that heat is travel in this direction, in one dimension, in this direction. Simultaneously the heat will get rejected to the surrounding because the temperature of fin is higher than the surrounding. So the convection takes place from the upper surface as well as lower surface of the fin. So heat conducted to the element. Let's take one small element from total fin, and the thickness of this element is taken as a dx. The distance of this element from the base wall is suppose x. So now Qx is the heat which is conducted from the base wall to this element. The thickness of this element is dx. So when a heat is entered in this element, the amount of heat is a Qx. While it travel this distance dx, some amount of heat is rejected to the environment by convection mode. So the whatever heat is exit from this point, it would be differ from the Qx. So let takes as Qx plus dx. Okay. Once again I repeat, let's the heat which will come from this base wall to this element by traveling distance x is Qx. This is the amount of heat which enter this element whose thickness is dx. So after traveling this distance dx, during that some amount of heat will be rejected to the environment by convection, by upper layer as well as by lower layer. So whatever heat is going to be exit from this element, it will be differ from the Qx. So let's take as a Qx plus dx because it travel x plus distance dx. So it will be Qx plus dx. So we know that the amount of heat which is conducted from this base wall to this element after covering distance x would be minus K dt by dx by Fourier's law. K is conductivity of this Finn's material, ACS is a cross-sectional area from which this heat conduction takes place, dt by dx is a temperature gradient, and x is a distance which traveled by this heat. Now heat conducted out of the element after covering distance x plus dx, it would be qx plus dx minus K ACS would remain same, dt by dx only, instead of x we will write x plus dx. And the third portion is Q convection. We know the convection mode of heat transfer, the amount of convection rate can be easily calculated by HA delta T, Newton's cooling equation, which is HA delta T. H is convective heat transfer coefficient. Now surface area of this element, so the surface area of this element would be its perimeter into its a thickness dx. So this is the P into dx, which is the surface area of this element. We are just talking about Q convection. This Q convection, the amount of heat rejected by convection mode only by this element. So it would be H, surface area of this element would be P into dx, its perimeter into its thickness dx, and the temperature difference. We don't know the exact value of the temperature at this element, so let's take as a T. The surrounding temperature is TA, so the temperature difference would be T minus TA, because we know the temperature of this element would be higher than the surrounding temperature. So this is T minus TA. Now applying energy balance equation, we know that amount of Qx is enter in this element, and from that Qx some portion of heat is rejected to the environment by convection mode, and some portion of heat is going to be exit from the element. So we can easily write down Qx is equal to Qx plus dx plus Q convection, because this is amount of heat which enters to the element, and from that amount some amount of heat is rejected to the environment, and the remaining amount of heat is going forward by the conduction mode. So we can easily write down Qx is equal to Qx plus dx plus Q convection. Okay. Now we know that from our previous slide that Qx is equal to this, Qx plus dx is equal to this, and Q convection is equal to this. So by putting this all three equation instead of Qx, Qx plus dx and Q convection, we will get this equation. Now we can simplify this equation. Minus K ACS dt by dx x plus dx. What is dt by dx x plus dx? So dt by dx x plus dx is dt by dx x plus change in dt by dx after traveling distance dx. Again, what is dt by dx x plus dx? It is amount of heat which is come after traveling distance x plus amount of heat which is going to be changed after traveling distance dx. So it is differentiation of dt by dx of x with respect to distance dx. So it is dt by dx x plus dx. So instead of dt by dx x plus dx, we can write this whole term. So replacing this term with this, we will get minus K ACS dt by dx x as it is, minus K ACS multiply with this, so we will get minus ACS dt by dx. Now if we multiply minus K ACS dt by minus K ACS with this equation, we will get minus ACS. This is dt by dx, this is also dt by dx, so it will be d2t by dx square, and into this dx will remain same, plus hpx t minus ta will remain same. Now we know that these two terms will cancel out. If we put this two term in this side of is equal to, we will get K ACS d2t by dx square dx minus hp dx t minus ta is equal to 0. So in this equation, let's divide whole equation by cross-sectional area ACS. So we will get more simplified equation like this. In this equation, let's again divide whole equation by K, then we will get this equation. Now let's make it more simple by considering this T minus TA as a theta. Let's equation can further simplified by transforming the dependent variable by defining the temperature axis as a theta. This is a temperature difference. Let's take theta x is equal to Tx minus Ta, because this is the temperature at distance x. So we can write as a Tx minus Ta. This is ambient temperature. So this is temperature difference at distance x. So we can write as a theta x is equal to Tx minus Ta. Differentiating this equation, so d theta by dx, dt by dx. This is ambient temperature, which is always constant. So the differentiation of this constant would be 0. Now again differentiate this equation, we would get d2 theta by dx square is equal to d2t by dx square. So now replacing this d2t by dx square by d2 theta by dx square minus hp by k ACS. This is a constant value. H convectivity transfer coefficient, P perimeter, K conductivity, and A cross sectional area. The product of this equation would be some constant. So let's take as a m square. So your equation would become like this. Instead of d2t by dx square, we can write d2 theta by dx square. Instead of hp by k, let's take m is equal to under root of hp k for simplification. So it would become m square, and T minus Ta can return as a theta. Why we do this? Let's understand. So our equation is d2 theta by dx square minus m square theta is equal to 0. This is a general form of energy equation for one-dimensional heat dissipation from an extended surface. We can see this is the second order differential equation. You can see this is a second order general solution of this linear homogeneous second order differential equation. This is a second order differential equation, and we know from the maths 3 that the solution of this equation can written as theta is equal to C1 e raised to mx plus C2 e raised to minus mx. This is the solution of this second order differential equation, where C1 and C2 are constant and need to be calculated from the boundary condition. Okay, so this is a general equation for any fin, any rectangular fin. In this equation, C1 and C2 are the constant and need to be determined by using proper boundary condition. So according to boundary condition, there are basically 3 cases. Case number 1, if the fin is infinite long and the temperature at the end of the fin is essentially that of the surrounding air. We can see that from, if the length of the fin is infinite long, after some length the temperature of the fin is nearly similar to the temperature of the surrounding. So this is a case number 1 where length of the fin is infinite. In case number 2, the end of the fin is insulated, and in case number 3, the length of the fin is supposed to be short, so that at the end there is a loss of heat by convection mode. So these are the 3 cases which we have to learn. So let's start with the case number 1. The fin is assumed to be infinitely long and the temperature at the end of the fin is essentially that of the surrounding air. Here in figure we can see that this is our wall whose base temperature is TO. One fin is attached with this wall. Here you can see that this is a symbol which shows that the length of the fin is infinite. This is the point where fin is attached with the wall. So this is a reference point, so taken as x is equal to 0. This is starting point of the fin, and at the end of the fin the length is infinite, so that at x is equal to L is equal to infinite. This is a temperature versus length profile at this point where fin is just attached with the base wall, so that at that point the temperature of the fin would be similar as the base temperature. So at x is equal to 0, the temperature of the fin would be TO, which is much higher. Now as we are moving from the left to right, as we are moving to this direction of the fin, the temperature would decrease, because whatever heat is conducted from the base material, it is that much of heat is going to reject simultaneously to the environment by convection mode, so that the temperature will reduce from left to right. So here we can see that there is a temperature drop along this direction, and after some length after some length from the base material, there would be no heat after conduction to loss to the environment, so that after some length the temperature of the fin material would same as the temperature of the ambient surrounding. So at x is equal to infinite, length, the temperature of the fin would be same as the ambient temperature, so that the TF. So this is the profile which shows the temperature drop along the fin from the left to right. So here we have two boundary conditions. First, at x is equal to 0, the temperature of the fin is nearly TO, so that the T is equal to TO. So that the temperature difference between fin and the environment would be TO minus TA. Okay, TO is the temperature of the fin and TA is ambient temperature. So the temperature difference theta can written as theta O, and theta O is equal to TO minus TA at x is equal to 0. This is our first boundary condition. Second boundary condition, at x is equal to infinite, the temperature of the fin is TA and the temperature difference would be TA minus TA, so that 0. So at x is equal to infinite, the temperature difference is 0. Okay, now by using these two boundary condition, we can easily find out the value of constant. We know our general equation for the fin is theta is equal to C1 e raised to mx plus C2 e raised to minus mx. Now putting boundary condition, we can easily find out value of this C1 and C2. Putting first boundary condition in this equation, at x is equal to 0, theta is equal to theta O. Putting x is equal to 0 in this equation, so it would become e raised to 0 1, and this e raised to 0 is equal to 1, and instead of theta we can write theta O. So this equation becomes C1 plus C2 is equal to theta O. This is our equation number 1. Let's put our second boundary condition in this equation, which is x is equal to infinite and theta is equal to 0. So theta is equal to 0, so that 0 e raised to infinite, and this will become e raised to minus infinite. So e raised to minus infinite means 0. So this whole term would become 0, and e raised to infinite is 1. So from this equation we can write down C1 is equal to 0. By putting value of C1 in this equation, we will get C2 is equal to theta O. Now putting this both values C1 and C2 in this equation, we will get theta is equal to this C1 is equal to 0, so that this term will become 0. Instead of C2 we can write theta O and e raised to m minus mx as it is. So this is our equation, theta is equal to theta O e raised to minus mx. Theta, instead of theta we can write t minus ta. Instead of theta O we can write down to minus ta e raised to minus mx. So this is the first equation which we are going to use in our numerical, that t minus ta upon to minus ta is equal to e raised to minus mx. In this equation, ta is ambient temperature, surrounding fluid temperature, to is our base temperature from which our fin is connected, and this t is the temperature at distance x. If we put at x is equal to 0, this t becomes to. At x is equal to infinite, this t becomes ta. So this temperature is dependent on the value of this x. At this particular distance, this value shows the temperature at this distance. So this is our first equation. But our final goal is to find out the amount of heat transfer rate if we use infinite long fin. So how to calculate heat flow rate across the base of the fin? We can calculate by calculating amount of heat conducted from this base wall. If we, I am going to repeat this once again. If we want to calculate how much amount of heat is going to be rejected by using this fin, so we want to calculate that amount just by calculating amount of heat conducted from this wall to the fin, because that much of amount can be rejected by the fin to the surrounding. The whichever amount fin will get from this wall by conduction, that much of amount of heat will rejected by the fin to the surrounding. So that's how we can calculate amount of heat lost by the fin. So to calculate how much amount of heat is conducted from this base wall to the fin, we have simple Fourier's equation of conduction, that minus k dt by dx. Here we are talking about this location, because whatever conduction takes place between fin and the base material, it will take at this plate, so that at x is equal to 0. So here I have written at x is equal to 0, dt by dx, the temperature difference at x is equal to 0, temperature gradient at x is equal to 0. K is a conductivity of this fin material. ACS is a cross-sectional area of this fin, because the larger the cross-section area, the more amount of heat can conducted from the base material. Now we know that from our previous slide that T minus TA upon TO minus TA is equal to e raised to minus mx. Okay, we want the equation for dt by dx, so we can differentiate this equation with respect to x. So it would become dt by dx. TA is constant, so its differentiation would become 0. TO minus TA is a constant, so differentiation of e raised to minus mx, e raised to something becomes e raised to something, so e raised to minus mx will remain same. Differentiation of minus mx, so it will give minus m. So differentiation of this equation would become dt by dx. At x is equal to 0, so I have written x is equal to 0, minus m TO minus TA e raised to minus mx. So we need to put x is equal to 0 in this equation. So if we put x is equal to 0, this would become e raised to 0, which is 1. So dt by dx at x is equal to 0 would be minus m TO minus TA. So replacing this value of dt by dx at x is equal to 0 in this equation with minus m TO minus TA, the equation would become minus k ACS would remain same, minus m TO minus TA instead of this. Now this minus and this minus will cancel out, it become plus, so k ACS m TO minus TA. In this equation we know the value of m square is hp by k, so m is under root of hp by k. So instead of m we can write under root of hp or ph by ka. Now this is k ACS, this is under root of k ACS, so the final equation will become under root of hp ka TO minus TA. This is the final equation for heat transfer rate for the infinite long fin. So this is our case number 1. In our next lecture we will discuss our case number 2 and case number 3. So that's it for today. Today we have learned introduction of extended surface fins, what is the purpose of fins, to increase the surface area, to get more to increase heat transfer rate by convection. We have learned general equation for the rectangular fin, and we have discussed case number 1, which is infinite long fin. That's it for today. Thank you so much.